finding the energy calculations and formulas, assuming when the car travels down the slope. So assuming that the velocity of car is 30 meters per second, height or elevation of the road is 50 meters, mass of the vehicle is 1000 kilograms. Now calculating the potential energy using the formula PE equals mgh and recording the results in joules, and calculating the kinetic energy using the formula Ke equals m half mv square and recording the result in joules. And finally, by adding the potential energy and the kinetic energy, I'm finding the total energy of the car, used by the car, and recording the results in joules.
In this iteration, a major task was to split the road.py file, which had about 2,000 lines of code, which was really hard to navigate and make some changes. If you have to make some changes, you have to scroll all the way down and do a search function, and it was really tedious. So we decided to break this file down into 7 or 8 different files, each having their own significance. So traffic will have its own, bend will, and elevation will have its own. So I proceeded with creating a road folder. This is the new one. And the road.py file, which had about 2,000 lines of code, now only had 120 odd lines. And each file had its own significance and functionality. So that made the code more readable and maintainable.
My deliverable for this iteration was to clean our dataset by finding any missing values, outliers, or any inconsistencies in our dataset. To start off with, the features in our dataset which has missing values can be seen in yellow, and out of these features, the key column which is more likely to be used in our model is IRI. Due to that, it was imputed using its medium value. Moving into find any outliers in our dataset, descriptive statistics was used to find the difference between the 75% quartile and the maximum of our numerical features. After having a look, we can see that curvature and IRI has significant difference between max and 75% quartile. In these box plots, you can see that there are few outliers for these features. To find out whether they are actual outliers or mistakes, a small Google search was done using its coordinates. After performing the search, we were able to find out that they were actual outliers. And this picture is an example for IRI's max value, which was 18.92. Similarly, went on to find out if there are uninformative or repetitive duplicates and inconsistent values in our dataset as well.
So in this iteration, I had to streamline, align, and make the graphs and the maps responsive that were present in the app, and just do some CSS. As you can see in the old version of the app, the maps are not aligned properly. One is in the left, one is in the right. Some of them are overlapping, and yeah. And now all the issues have been fixed in our app. As you can see, um, now it is all pretty much streamlined and as well as responsive to the relative screen size of the user.
This is Ken. So basically this past iteration I've been mainly working with energy calculations and forces. So for a car in this scenario, going with changes in speed and changes in elevation, basically dealing with the mechanical energy, which consists of potential and kinetic. So we have the formulas for both of them. The changes in potential energy plus changes in kinetic energy would be the total amount of work done and work done by the car, and that's what we're going to be dealing with. Secondly, coming to forces, we've got two mainly restrictive forces acting on the car. The first is air drag. Air drag is more related to fluid dynamics. I haven't looked too much into it, but the one that's more concerning for us is the rolling friction, because that's where the IRI values come in. So the IRI, the roughness of the road, we have the values for that, and if there's a higher IRI value, that's going to increase the rolling resistance coefficient. That's right here. So that's if we have a higher coefficient, that's going to increase the rolling resistance for that force that's acting on the car.
So based on the discussion with our client, we had to work on creating driving scenarios. In this iteration, our focus was to research and get started with the development. I was responsible for this task, so I started with researching ways to do the same, and I was able to find a solution that looked promising in serving the purpose. This is the Driving Scenario Designer app in MATLAB. I created a simple driving scenario to test the app. I've considered the bends and curves in the road and have adjusted the speed of the vehicle accordingly. This simulation will help us to understand the vehicle's speed, and as we can see here, the speed of the car reduces whenever there is a curve in the road. This was just an initial test of the app, and our next challenge will be to import the actual road data that we have collected and use it to create some driving scenarios.